where we want to focus on Ethernet switching, which is all a layer 2 thing. Layer 2, or the data link layer, is unique from all of the layers because it is the only one that really has subparts associated with it, and particular the LLC layer and the MAC sublayer or MAC sublayer. The real key thing that happens at the data link layer is this is where our packets are going to be encapsulated or de-encapsulated, and we're going to make frames. This is where the physical network addressing is implemented, and also the topology is really defined or implemented, whichever way you want to look at it, at the data link layer. And the Ethernet switch is our common building block that is used at that layer. Again, the sublayers, particularly, again, different functionality. Primarily, we want to focus on the MAC sublayer. Again, just some details of what fundamentally happens. And the frame, remember, is our PDU. Now, there's 4 types of standardized frames that exist, of Ethernet frames. Remember, when we talk about frames, we're going to assume we're talking about Ethernet frames. The differences have evolved over time. Different frame types can exist on a network. However, let's think back to our basic network model of the send host and the receive host. Those 2 hosts must be configured for the same frame type, okay? There's no backwards or upwards compatibility, but you could have multiple frame types on a network, and sometimes that is done because there's often a mix of, let's say, some legacy stuff and some more modern host devices on a network. There also is non-standard Ethernet frames or proprietary stuff. Anyone have, well, I hope you don't have still, but have had, let's say, a Grass Valley System 7000 routing switcher, or seen one, know what that is? They used for the interconnectivity between the control system and the control panels. That's basically Ethernet, but it was a proprietary implementation of Ethernet. So again, there can be. Ethernet 2, however, is the common standard today used in the Ethernet environment. You also might find that referred to as the DICS frame format. Where in the world does that come from? Well, that's an acronym that stands for Digital Equipment, Intel, and Xerox, which of course were the original developers of that standard. One thing I don't think I've mentioned, I think it's the terms are on the slides, but looking at standards, there's 2 types of standards. There's de jure and de facto standards. De facto standards are those that are generated by a standards body. The de jure standards are simply standards that become standards because they're popular, have been implemented. In other words, the industry has implemented to do it this way. It's become a standard. We think of it as a standard, but it doesn't have this standards body. Ethernet 2 was one of those because it was developed by a consortium of, at the time, major computer equipment manufacturers, DEC, Intel, and Xerox. Okay? Interesting that effectively 2 of those are gone from the industry. Only Intel remains. But anyway, major players in the industry developed this is the way it was going to do it, and it became the way. Looking at the details, and I jumped ahead here, with that frame, certainly we're most often concerned with the data or the payload data. A couple of things to note is that the size of the payload data has limits. It has a lower limit and it has an upper limit associated with it, which means the information must be packaged into a certain format within that PDU. Layer 2 is also where the first error checking is performed. That's done by adding a CRC value at the end of the frame. And then, of course, we have some other fields. We'll talk about a couple of these that, again, is part of that overall header information. Because of the minimum or maximum size, if we take and add the header information to it, that defines a minimum and maximum size that a Ethernet frame can be, right? We take the minimum maximum of the payload, add the header information, we define a minimum and maximum for the overall frame. If we have a frame that is smaller than that minimum size, that's referred to as a runt frame. If we have a frame that is too big, it's referred to as a giant frame. Either one of those conditions occur because some errored condition happened that impacted the size of that frame, but they are simply errored frames. However, one of the things we don't want to do is confuse a giant frame with a jumbo frame. A jumbo frame is a valid frame format. We'll talk about what makes it special in just a moment. And another thing to keep in mind is the preamble. The size of the preamble is not utilized in that frame length calculation. Again, some of this content is used for certification, prepping for a certification test. You can really make some confusing questions about some of these details. I shouldn't say confusing, challenging questions. Again, let's not confuse a giant frame, which is an errored frame, with a jumbo frame, which is a valid frame. And a jumbo frame is simply a frame that now we have increased the payload up to 9,000 bytes, okay? Basically 6 times as big, okay? Why do we want to do something like that? Well, we do that for efficiency. Jumbo frames are typically used for information that is considered large data sets, or big data is a term that's often used in that. That usually is very, very large database type files, or visualization files, or certainly that could be HD video would fit that application. And we do that for efficiency. And think about the efficiency with a 1500 byte frame, in other words, the payload, and you take the header information. The header information is fixed, so you have about a 3% that's dedicated to the header. We can have better efficiency with a jumbo frame because the header is the same. We're just going to send more information. However, jumbo frames can create problems. They create problems because often not all of my network infrastructure equipment can recognize a jumbo frame. If it can't recognize a jumbo frame, it's going to what? Be interpreted as a giant frame, which is an errored condition. And what does an Ethernet switch do with an errored frame? Throws it away. It's gone, okay? Think, well, that's not good, is it? That's information. It's gone. Well, think about now the OSI model, the layered approach. Each layer has a specific function and a place. In that situation, we have a frame that's discarded. What happens? We need all of our frames to reconstruct what? Just application data? Well, that's not layer 2's problem. The problem is passed on to the next layer to deal with that. Okay, and we'll talk about how that's done. But that's part of the architecture of that OSI model. So again, the challenge is not all network devices, and it's not necessary of new versus old. It is Could be two brand new two brand new different models even from the same manufacturer, and from the feature set, the cheaper one maybe does not handle jumbo frames. So one of those details to be aware of if you're in an environment that should be using jumbo frames. Again, I'd mentioned one of the key features are performed at layer 2 is the physical addressing. That's done through the media access control address, or the MAC address, which is a 6-byte hexadecimal notated address. It's like the serial number. It's burned into the network adapter. Thus, the source address that you find within the header information. I also equate that, it's like the VIN number of your automobile. It's a unique address for that device. Certainly we know that we can take an automobile VIN number and we can decode that VIN number, right? And you can find out all kinds of interesting things about your automobile. You go to the body shop to get your car repainted. What do they don't care what color you want it. They're going to, if you say, I want it the same color, they said, okay, all they're interested in is the VIN number, because they can decode that and find out specifically what that paint was used. You can find out what feature, there's all kinds of information. Similar with a MAC address, although a little simpler, that MAC address is split down the middle to an organizational unique identifier, or a OUI, that can be traced back to a manufacturer. So if you have a network and you have a bunch of host devices and you've identified one particular host that maybe is a problem, but you really don't have a clue what it is, often by decoding the MAC address, you might give you at least narrowed down the set of host devices. Again, it's split simply down the middle, and I'll give you some references to look up the different OUIs. In this particular example, this actual MAC address, A46706, AB41D5, can be decoded. The OUI is registered to Apple, so that would obviously tell you that is potentially a Apple device, which this particular one came from an iPad. MAC addresses have a standardized format that they're expressed in. It is a 48-bit address expressed as 6 hexadecimal digits separated with the colon is the way the standard says. However, we will find manufacturers that will express them in different formats. Okay? It doesn't really change anything other than maybe add a little confusion to some. It's still 6 hexadecimal digits. The first 24 bits of those is still the OUI. None of that changes. It's just how it is expressed. And finally, if we have a MAC address of all ones, which expressed hexadecimally is all FFs for each of those digits, that is a broadcast MAC address. If you think about a host adapter, a network adapter and a host device, what does that adapter do? Well, one of the things, it listens to the network, and it really only listens for 2 things. Again, we're at layer 2. It's going to be listening for a destination MAC address that matches its own source address, or it listens for the broadcast address. Any other traffic on the network, that adapter is going to ignore. Okay? However, if the broadcast address is heard or its address is heard, it's going to then take and pass that information where? It's going to pass it to the next layer, to layer 3. Again, everything else is ignored. Let's talk about collision domains. think Wiley had asked a question earlier about collisions. Collisions came from the bus-structured world, or any situation where we have more than two devices on a network segment. Okay? As we evolved or moved from the bus-structured world of coaxial Ethernet to the point-to-point or star configuration associated with current network where we're utilizing switches, one of the advantages we're able to minimize the collision domain or eliminate collisions. And we do that by only attaching one host device to a network switch. Now that doesn't say we cannot connect a hub device to a network switch ports and of course hook multiple host devices to the hub. This is a common practice in years past. Today, that is something, because of the cost of Ethernet switch ports, that's something we don't want to do, because when we do that, we have created, again, each of these collision domains. The ideal collision domain is only one host. If there's one host, there is no contention for that bandwidth, right? Whereas over here, we have contention for this bandwidth from these three hosts, and also it's going to cause us to either configure or let the auto configuration is going to take this connection. It's going to automatically put it into the half duplex mode, and it's going to downgrade the speed to the maximum capacity or the lowest capacity host device. So it's a way to degrade our performance and so forth. So let's talk about switches. When we talk about switches, there's really kind of two pretty distinct categories we want to put those in, is managed switches and unmanaged switches. The unmanaged ones are what I'm going to call the consumer-oriented switches, generally categorized as being lower cost, plug and play, which says they also have a fixed configuration to them. They do the basic functions of an Ethernet switch, which we'll talk about what those are in a minute. There's also the managed switch, which has a feature sets associated with it, has the ability for the user to configure that switch. And with that, that means you have access to monitor the switch actions. Managed switches also have additional features that allow you to maybe implement VLANs, and we'll talk about some of that stuff as well. In our context, we're going to be referring to managed switches because, quite honestly, in a broadcast or professional environment, that's really where you want to be, particularly if it's anything within the core part of the network or within the network that is supporting the what I'm going to call the broadcast plant. Now, that doesn't mean we're not going to have unmanaged switches, that probably exist and so forth. However, now I want to call you one that sort of muddies the water up a little bit. Used to be really distinct categories. You could tell the price. I know that's an unmanaged switch because of the cost of it. Okay? There's a series of switch, and it is a specific series by the model number of what is referred to as a web-managed switch that comes from, and this particularly is a Netgear one, and that's a term they use, that is sort of somewhere in between. So it muddies up the water to make that distinction. Particularly, it's gigabit capable. One of the key things it has port mirroring, which we'll talk about in a little bit of why that might be handy. It has a cable check, a little small TDR built in it, basic continuity check built in. You can implement VLANs in this switch. And the last time I looked at one on Amazon, I think they were $34.95 for the small 5-port version and so forth. So again, be aware that exists. But again, kind of as we move on, everything we talk about switches are going to really be in the context of a managed switch.
Okay, Wayne, you say it's web managed. All other managed switches can also be managed by the web too. So
Yes.
why would you call it web managed? Shouldn't you just
That is Netgear's term that they use for it. So,
okay, so it's basically a limited feature set
Yes.
switch. Okay.
yeah, and that's why I mean it's muddied the water, which used to be these really two distinct classes, and I could tell you that's a unmanaged switch because it costs $29.95 or $99.95 for maybe a multi-port one, and this other switch that looks just like it is $399, or maybe $3,099 if it says Cisco on it, or whatever. Again, it's clouded. The Netgear stuff is clouded. But that one, if you have a little, everybody, Larry has this little suitcase over here that's got all kinds of audio adapters and cables and gadgets and gizmos in it. We all have one of those, right? Because of the dominance of networking, you're probably already if you already don't, you're putting together or will develop kind of that same little kit of stuff to troubleshoot network problems. Could be as simple as a crossover adapter or a crossover cable, but, some stuff. If you're building one of these, this is something really handy in terms of a troubleshooting to add, particularly if nothing else because of the port mirroring, and we'll talk about port mirroring in just a moment. But anyway, Ethernet switching, originally referred to as bridging. If we go back to those IEEE standards documents and read through those, we'll see all reference to bridging. Well, they're referring to switching. Ethernet switching is transparent. Remember, we're at layer 2. The PDU is the frame. By transparent, that says the frames are not modified. Okay? In other words, they're going to pass from an ingress port to either a single egress port, or in a couple of unique situations, all other ports, but the frames are not modified. If a frame is errored, we've already talked about what happens there. It's dropped. Well, that's not modifying it. That's getting rid of it, right? So the contents are not really changed. Well, not quite so true. We'll talk about that situation where they are. But they are transparent. There's two types of modes. One is referred to as store and forward. The other is cut through. Store and forward is the normal, what I'll call the normal operation mode of the switch, where, again, if that frame is errored, it's determined errored to be either what? Either the link is too big or too small, or it's got CRC errors that have been detected because the CRC value and the payload contents do not match up. So it's dropped. Or there's cut through, which simply reads the header. Because to make the, quote, switching or bridging decision, all the switch needs to do is what? Look at the destination MAC address, and that's all it does in the cut through mode. Thus, it's faster. That's why that mode was developed. Well, today, because of the, technology advancements in silicon and all of that, I don't know that necessarily holds true anymore, that it is faster, but it's not that much faster. So for the most part, I think you will find store and forward commonly used, but be aware that cut through does exist. What that really says is I could be switching errored frames, okay, and not necessarily know it. There really also is a third sort of a hybrid between store and forward and cut through that actually, instead of it looks at really the entire header and the first part of the data to be intact and again, it's probably you're not going to necessarily find that one. But I think for most part, you can assume store and forward is used unless you have some special application that you need to enable the cut through in a managed switch. Switches, the key thing they do to us or do for us is allow to segment the network. In other words, we can take and we can establish dedicated bandwidth between the switch port and the host interface port. We can increase performance because we've eliminated the possibility of any collisions. We've increased performance because we've guaranteed full duplex operation between the switch port and the host port. And this allows us then to implement or take advantage of some security capabilities, which we'll, of course, talk about security capabilities. Again, switches simply selectively forward individual frames from a receive port or an ingress port to a specific destination port. Yes, sir.
Question. Back to the way it's stored forward and cut through. In the application where you didn't have a managed switch and it's one of the plug and play switches, do they normally do one or the other?
They will, I think,
They normally
I'm going to say 100% you can be assured it's doing store and forward.
stored forward.
Yes. So it's what that says is it's going to drop an errored frame. Okay.
Okay, I got follow up. Define an uplink port on a small switch where you might have an uplink.
Let me defer that question to a few more slides. Okay. I'll just comment. That's a term that can mean different things in different applications. Okay. And we'll talk about that in just a minute, I think. I hope we will cover that adequately in a couple of minutes. So anyway, we're going to selectively forward frames from an ingress port to a egress port. So if we look at all the functions of Ethernet switches, and of course Ethernet switches come in all kinds of physical forms and varieties and manufacturers. We can go down the store to the local Walmart, right, and buy an Ethernet switch without any problems. We can go to, wide variety of different places. There are several functions that any Ethernet switch does, whether it's the $29.95 one that we buy at Walmart or the, $5,000 industrial automation control Ethernet switch. Again, they all do some basic things, and that is they learn MAC addresses, they build a table of those MAC addresses to associate what MAC address is on what port of the switch. Ideally, we want one host per switch port, right? But if we should have more than one, then it's going to build, that'll be so contained in the table. In other words, what MAC address or addresses are on an individual switch port. It's going to filter or forward Ethernet frames, okay? Ideally, forward them. And in a unique or one situation, it's going to flood Ethernet frames. Okay, flood means it's going to send that frame to every port on the switch except the port that frame came in on. So if I have a host connected to port 1, here's a frame, it's going to, by flooding it, I'm going to send it to every other port except port 1. And I can have Ethernet switches, and this is where we get into the managed side of the house, that have other features. There can be a lot of other features, but generally those will fall into probably 3 general categories of loop avoidance. In other words, I can implement redundancy in my connectivity. There can be security features. There can be multicast features. There might be or likely will be some quality of service features. And again, if I'm here to sell you switches, there's all kinds of different sometimes optional type services that can be implemented through software. This is my version of how to build an Ethernet switch, okay? Simplified. Although Ethernet switches today are really pretty, what are they? They're really based upon silicon, and there's sort of some basic building blocks out there. If we were going to build a Ethernet switch today, we would pick a chipset from maybe we're going to use a TI chipset, and we would build that in a very similar block function. But what you will find, regardless of the deals, we have, again, a host connected to a port. We talked about maybe we have PoE capability. So if we do, we have to inject that DC voltage. So we got to have some electronics to do that. We're going to have what is generically referred to as a port Asic, which within that silicon is going to be some processing, and we're going to have egress and ingress buffers. In other words, some temporary memory. We're going to have a backplane where we connect everything together, and then there's going to be, of course, a central control processor, and there's going to be the MAC address table. In other words, some memory allocated where that MAC address table is going to be contained, which often is referred to in an Ethernet switch as a CAM table, because content addressable memory is used, which is slightly different concept than regular random access memory that we're probably most familiar with. Think about a RAM or random access memory is commonly you provide an address, the memory returns information from that address, right? It has a read cycle, could have a write cycle. You specify an address, put this information in it, okay? But it's this random, you supply addresses, you get information back. In a CAM table, or content addressable memory, I'm going to specify the contents of the memory. You tell me where it's at. Because what is going to be specified is a MAC address. I want to know where this MAC address is. Okay? Tell me where it's located. So that's really kind of the difference in the two. And thus, again, an Ethernet switch is going to take a frame from an ingress report or ingress port. It's going to look up that destination MAC address from the CAM table, and it's going to then forward that frame to the appropriate egress port. What happens, however, if that destination MAC address is not in the CAM table? That is the situation where the switch then is going to flood that frame to all of the ports except the ingress port. Okay? Assuming the host really exists, that host will respond. Then the switch is going to be able to capture its source address, which goes in the CAM table, and it's then maintained. Again, the broadcast address is the other one where it's simply because the destination is the broadcast address, it will be forwarded again to all ports except, of course, the ingress port. So there's really only two situations where a switch will flood. It will flood based on the broadcast address, or it will flood if a MAC address is not within the CAM table.
Question.
Yes, sir.
I thought about this a minute ago and hit it. If you were in a situation where, all right, let's say I've got a switch and I'm out of ports, so I go buy another switch and I've used two switches and I just tie the two switches together. So that'd be a situation where it would really slow down because of the CAM table, because it's going to have to flood from one to the other every time it crosses over.
Not an ideal way to do it, although it might be a perfectly acceptable way to do it. And it really depends on what kind of activity is going on between those two.
But it would create some
switches.
delay and
Yep.
really shouldn't have any loss, but it would be a throughput.
It could be a
Bottleneck.
throughput. That's right. But if all these hosts are doing relatively low bandwidth stuff, might not be a problem. And let's take a radio. I often use radio stations as a basic example. You have, the administrative computers and stuff. That might work just fine in that environment, of the office environment. Again, I get into my technical plant, that might not work so well, because I'm often dealing with what? I'm dealing with media, real-time media streams and that sort of thing. So it might not work too much in there. On the other hand, if my broadcast plant really is only using network for control functions, maybe a basic small automation system might work just fine. So it's one of those that does depend.
Wouldn't it only, in his example, it would only have that flood situation when it didn't know what something was
Right.
new? Once it figures out what everybody is, then that's not an issue anymore, is it?
Well, but again, because now you're going to have now multiple devices on one of those, on a port. There's going to be contention for that bandwidth. So ideally, we go back to kind of your question about an uplink port. Generally, uplink reports are ones that were utilized, they have higher bandwidth because they're used to link to something else. But you could take, let's say, these $29, I keep calling them $29 Walmart switches.
You're in my plan now, go ahead.
And there probably is, say, a 6 or 8 port switch. Maybe that's your 2 switches, and you just use a crossover cable, unless your switches have auto configuration that will configure one of those ports as a crossover to use a straight through cable. And what you've done, think about now, there's going to be multiple MAC addresses on those 2 shared ports, so it can find where it is. Also, of course, connected, there can be, again, auto negotiation, duplex and speed, which is pretty common in most switches today. Although in a managed switch, you can also go and override that, which there are times you might want to do that because auto configuration doesn't work all the time. Even the specs say it should. It doesn't necessarily do that. There's also the audio media dependent interface crossover. This again is configuring that port as straight through or a crossover. So again, there's typically other features associated with the port.
And you talked about auto negotiating down. There's been a lot of issues with ubiquities getting RF and the LAN cable coming down and auto negotiating it down.
I have a general, rule of thumb that on network infrastructure that you don't use auto negotiation, you hard set everything. And that's okay to use auto negotiation in the office LAN for, a desktop computer talking, but in the broadcast plant, I'm a proponent of hard setting things and not relying on auto negotiation.
Radios and ubiquities, you can't tell it not to auto negotiate on their end or something.
Okay,
I'm not sure what
then
the
in your
deal is
managed
there.
switch, you hard set it on that end.
Here's a multicast thing that we have here in Alabama. We have a satellite network that delivers EAS, and it comes out of the receiver as a multicast IP, and then in the individual EAS boxes, we set that up to listen on that particular port. In that case, when it comes in and is plugged into the LAN, it does flood all the ports, but only the devices that we have put that in that it listen on is the only ones that receive it. Mm-hmm. But yet it is going to all the other devices, since on multicast it does go all the ports. Is that correct?
Depends.
Okay.
You're going to hear me use that answer for a lot of things. It depends. It depends on the switch. And we'll talk about that, I think, in a few more slides. Hopefully I'll address Wiley's question about uplink ports, and I'll address that one in a couple more slides. So again, we build a MAC address table or a CAM table, what we call it. Typically, it's going to it's going to have a MAC address there. It's going to have a port. It's also going to have an aging metric associated with it, which is basically a timer that says how long will that MAC address remain in the table. Okay? And there are different defaults. 300 seconds is a pretty common value. Managed switch, you can also change that value. Okay? And when the aging timer expires, what happens? Well, that MAC address is just automatically erased. Again, kind of a general format. This is what a real address table looks like, or at least a real Cisco from one of their displays. And a couple of things I just want to point out. Notice the format of the MAC address. That looks a little different, right? Remember the comment about some manufacturers choose to put MAC addresses in different formats? Well, the second one on the list is the way Cisco does it. And the third one, if you remember that one, that's the way Microsoft does it. Okay? So, the big guys in the industry, they can sort of do what they want to. But nothing really changes the fact the first half of this MAC address is the OUI, and the other remaining 24 bits is that unique serialized identifier. Again, this is not the actual table. This is the Cisco way of displaying that theoretical table. Of course, using their port designation, Fast Ethernet port 0/14, again, is their nomenclature. The other thing to point out, the word dynamic, that says that was a learned address. So that address was learned from a host connected, in this first one, it was connected to port 14. That address was learned. Note, every address is a member of VLAN 1. Well, VLAN 1 is special. Every Ethernet switch has a VLAN 1. Even our $29.95 Walmart switch has a VLAN 1 to it. And because that is not a managed switch, we can't change that. It's a fixed configuration. So all our hosts are in a member of VLAN 1. It's commonly referred to as the default VLAN, and it contains control plane, and that should say plane, not plan, traffic or information plus the user data. When we talk about security stuff later, one of our practices is we don't want to use VLAN 1, because if I'm a hacker trying to do something nasty, that's the first place I'm going to go, because even this $3,000 or maybe the $10,000 Cisco managed switch, its default configuration is probably going to have all the ports enabled and everybody's a member of VLAN 1. That's just a common default configuration. Okay, because we can segment, use an Ethernet switch to segment or separate host devices, one of our advantages is to create VLANs, or virtual local area networks, between those host devices. In other words, we can segment host devices, and then we can connect those through VLANs, which are basically isolated virtual networks but share a common physical medium, whatever that physical medium may be. Or in most cases, the physical medium is also is often a mixture of things, right? We have twisted pair, we have fiber, and we might have some wire. We might have all three of those in an end-to-end network, and we can transport those VLANs. Generally, two types of VLANs: static port, which are the most common. These are basically manually configured. There also can be dynamic port ones that are, as the name implies, they're automatically configured based upon some type of criteria. That criteria is often the MAC address itself. In other words, because I have the MAC address, I've identified what host device that is, or maybe what type it is, and I'm going to automatically associate that host with a certain VLAN, commonly done in voice over and telephone, voice over IP type systems. I have a desk set that's really a host in terms of the network, and because I know its MAC address, I know that is a certain desk set with certain features, and I'll automatically make that host device a member of the, say, the voice over IP VLAN. Or I might do that on a protocol basis as well. The key thing to remember about a VLAN, okay, the traffic or the data between the host and that VLAN are in that VLAN. Even if I'm sharing a same physical network medium, the other host and their information in another VLAN is separated. Okay, there is no crossover between those. Now, keep in mind, however, that the physical bandwidth, there's no free lunch here. Okay, I can't build a bunch of VLANs that all, I have to keep in mind the physical capacity of my medium. Okay, so I can't just stack a bunch of VLANs that's got who knows how much traffic. So you have to keep that physical side in mind. But again, there's no interaction between the host devices and those VLANs. So as an example, let's build a little network. We'll start out and let's take 3 switches and put together a small network that looks like this, and let's use 3 VLANs. Now, one thing, I keep saying I'm going to change the slide because I'm probably implying something in this slide that is not accurate. I have configured the ports on each of these switches identically, right? In other words, I've taken the top ports on this switch and I've configured them to be a member of VLAN 1. I've done the same thing on each switch. Do not let that imply that's how it has to be done, okay? I did that because I guess I was lazy when I made the slide and do some cutting and pasting. I really do need to change that because the ports can be assigned any way you so desire. So let's build this small network. We're going to deploy these switches in different parts of our physical facility, and that's one of the advantages of the VLANs is I can distribute these switches in different parts of my facility. Maybe this is the engineering room switch, this is the first floor switch, this is maybe back in the news department, or however it might work. And again, we could certainly have more than 3 switches. When we build VLANs, we have 2 types of ports. Well, switches have 2 types of ports. We have an access port, which is a port designed for a host to connect to. We also might call that a untagged port because there's 2 nomenclature vocabularies that's used in the industry. There's the Cisco vocabulary, and of course they're the 1,000-pound gorilla in the room. But then there is what often is referred to as the HP, the Comware, the 3Com terminology, which quite honestly is in line more with the terminology that's in the standards documents than the Cisco is. But so keep that in mind. So that's why you see the two different types. When we have a port that's going to connect to another device, in this case an Ethernet switch, that is going to transport multiple VLANs, it's referred to as a trunk port or a tagged port in the HP or 3Com terminology. When we build this, we have created basically 3 broadcast domains. Remember, we had a collision domain that was associated with Ethernet switch segments. Okay? We have a broadcast domain which defines how far a broadcast from a host will travel. So in our example, we, regardless of where those switches may be physically located or the individual hosts are located, we have created basically 3 separate networks, okay, with the appropriate host devices part of that network. That network is considered a broadcast domain. In other words, a broadcast from this host will be heard by these 2 hosts, but it will go no further. Nobody over in this VLAN or the other one will hear that. And there, of course, as we've said, there's no connectivity between those networks. Again, to implement from a configuration standpoint, depending upon what manufacturer's equipment I have, will determine what what terminology I use. And by the way, regardless of what manufacturer's equipment, I think you'll find that a manufacturer will use one of those 2 vocabularies in their configuration. So let's say you have a I don't know, what's a Netgear switch. They're going to use pretty much the ComWare or the 3Com terminology as opposed to the Cisco. Some of them you'll find they'll use some from both. So it's a way to confuse everyone, if nothing else. But anyway, you'll make the appropriate configuration. So what happens, how do we know a frame what VLAN it is associated of or a member of? If I send a frame from this host, which is a member of the blue VLAN, to this switch that needs to go, let's say, to that blue host, how does the switch know what to do with it? Okay? Because if you remember the frame format, there was nothing in there that said anything about VLANs, in that header information, just destination MAC addresses and stuff. Well, what has happened? A tag is inserted. On the egress interface, we're going to insert a tag to associate that frame with a specific VLAN. When it gets to the ingress interface here, that tag is removed, and of course that frame then is directed to the appropriate port. This is an example where now we are going to modify a frame. Remember I said switching or bridging was transparent because we don't modify the contents? Well, this is a situation where we are going to modify it. And we're going to modify it by we're going to insert a VLAN tag into the header information. Okay? Particularly, we're going to insert an 802.1q tag. Thus, now we're going to make that frame now is going to become an 802.1q Ethernet frame, which implies to us that is what? A tagged Ethernet frame. Within the tag, there's some information. There's some header information that also identifies that's an 801.q tag. There's some, I think it is 3 bits that are for priority, so you could utilize in a quality of service to prioritize this frame. And then primarily there is the VLAN ID, which is basically the identifier of of that tag. And oh, by the way, because we've changed the size of the frame, what do we have to do? Have to calculate a new CRC, right? Because we've changed now, we've made that frame longer. You might find double and even triple tagging. That is not uncommon to find. You typically would find that maybe in an environment where you're getting some connectivity from a carrier or maybe from a corporate network environment or so forth. So you just basically stack tags, and you have what is referred to as the inner tag, and then outer tags that are added to that, and they're simply added to the left. So they're conceivably, if you had a triple tagged frame, they would simply be 3 tag fields that are there. Looking down a little bit more at some of the details, again, what we're really most concerned about is the Vlan Identifier. We have 12 bits we can work with, and we can all do by, we can all take 2 and raise it to the 12th power in our head, right? Okay. Well, that gives us about 4,000 and something possible VLAN combinations. Although there's a few of those VLAN identifiers that are reserved, so we don't get to use all 4,000, and I think it's 4,096 without looking it up. Larry's got his calculator, he's going to tell us, and we take out a few of those, but there's a good 4,000, VLAN tags we can possibly use. But another little gotcha, just because the standard lets you support 4,000 VLAN tags, that doesn't mean all the network devices are going to can support 4,000. In fact, most do not, unless it's a really high-end core switch. 4,096. Thank you, Larry. So we take our 4,096, we take out the reserved ones, which is a handful. There's still, again, over 4,000 tags that are available. A common number is maybe 10,024 is a real popular number that most Ethernet switches support. And I can assure you that's a lot of VLANs. One of the problems with VLANs is the management of those VLANs and the configuration. And I would not want to wish that on anyone that had to manually support 4,000, VLANs on a network. Also, be aware they are proprietary VLANs that exist. We're referring to 802.1q. That instantly, what does that tell you? That's an IEEE standard. Thus, if I have a Cisco switch, I ought to be able to build a VLAN to my HP switch and build a VLAN over to my Ubiquity switch, okay, or whatever the manufacturer should be. But they are proprietary ones that exist out there as well. Just be aware of those, which is obviously going to lock me into a specific manufacturer's product. So let's real quickly build a bunch of VLANs. Certainly we could just build separate networks. I remember the first time that we implemented digital audio for an automation system in our facility, I built just a separate network. I used all blue, or I used different colored jumper cables to tell. I had a red network and a blue network, okay? Probably remember red networks and blue networks from way back in the early days. That was my logic to keep up. And I just built separate networks, separate switches, separate wiring everywhere, okay? And that sort of fits this model. I could do the same thing, okay, with simply building what? Configuring 2 VLANs on this switch and do the same thing. And of course, I could expand that to different areas of the building or whatever, and I could link switches together with individual cables for a VLAN, but why would I want to do that? I could establish trunk links or tagged links between those 2, right? Now remember, maybe there's no connectivity between those VLANs, but maybe we need some connectivity. So what do? We add a layer 3 router. Now we're kind of jumping ahead because we haven't talked about routing yet. And I can link, of course, VLANs, take an individual port from a switch into an individual port of a router. Okay. I also could do that with one cable. That could be a twisted pair cable. That could be fiber optics. I would use, of course, a trunk or a tagged interface on my switch side, right? But there is no such thing on a layer 3 router, but there is a virtual interface. I can use sub-interfaces, and when we get to our configuration section, we'll talk that. So again, some really, really simplified ways of building a network. And oh, by the way, there are some servers, particularly servers that are used in a virtualized environment that also have trunk type interfaces or virtual interfaces on them. So I can, again, have and think about a virtual server. That server is going to need to have multiple IP addresses to support those different applications. So again, just some real quickie examples. Well, let's take our little network we built earlier a little bit further. Redundancy is always good, right? We're broadcast engineers. We're belt and suspenders type people, right? Okay, so with this configuration, I could simply add an additional connectivity between these two ports on these two switches, and I've created a ring architecture, right? I've provided redundancy. Okay? However, redundancy is a problem. Okay? Because now we've created a feedback loop. Very similar that Larry's maybe about to create with his microphone that he could. But we can create a feedback loop of what? Ethernet frames by doing this. In fact, if you want to break a network, that's a pretty easy way to break a network, okay? If you want to cause some grief, take an Ethernet cable and just plug it into 2 ports of a regular switch. You will create havoc.
Unless it's a smart managed switch that knows better and shuts ports down?
Yes, that's where we're headed there. We have to have a managed switch that basically implements spanning tree or STP, which is a protocol, again, because we are at layer 2, it's an IEEE bridging, part of the bridging standards, that basically prevents forwarding loops, okay? Because our basic design standards requires there's only one path between host devices. And these forwarding loops, what happens is they basically circulate frames. It increases unnecessary traffic, but eventually it will overflow the MAC table size. We didn't really talk about MAC table sizes, but depending upon the model of the switch, there's only so much RAM.
Then what happens?
This happens. Well, when you overflow a CAM table, yeah, what happens? The switch reboots. Okay? How long does it take for a switch to reboot?
Depends.
There you go. Depends on the switch. Some of the higher end Cisco switches, it takes nearly 5 minutes for one of them to reboot. Okay, my little 2995 switch probably reboots in, 30, 40 seconds maybe. And the high end Cisco takes 5 minutes, and if you're sitting there waiting and watching it, I swear it takes 10 minutes, But needless to say, the network is not working while that switch reboots. And all of a sudden it reboots and the network's working. And then before I know it, the network's not working and the switch reboots. So it's this cyclical pattern. And it really is a way to bring a network, to its knees, so to speak. So anyway, this spanning tree protocol. And because it uses the analysis of a tree, you start what a tree begins what? At the roots, to the trunk, to the branches, and finally out to the leaves. Okay? That's where you'll see all the that's where you'll find all the terminology. Thus, what we're going to do is we're going to prune ports to utilize. Now, in general, spanning tree on switches is enabled by default. Again, we're talking a managed switch. Okay? And there is information, particularly bridge protocol data units that are exchanged between these switches to basically prune the ports. Some kind of details I will not get into. So what happens? We build a network and I put in multiple links, which is good, right? Redundancy is good. But I've created a whole bunch of loops, right? So spanning tree is going to prune the links. And it's going to do that by establishing what is referred to as a root bridge. That can happen automatically, but in most cases, because this is a managed switch, I'm going to specify a root bridge. Generally, you're going to make that a kind of a core bridge of the network. But there's all kinds of interesting fallbacks in most of the algorithms. If let's say the first switch that comes online automatically can become the root bridge. But what if somehow I can turn all the switches on at the same time? Maybe they're on a power strip. I turn them all and they all come on at the same time. Well, who's going to be the root? Well, there's also a fallback in the spanning tree algorithm that says the bridge with the lowest MAC address becomes the root bridge. Okay? Again, probably instead of using the defaults, I'm going to probably hard set, in this example, say switch A, I would make that maybe my root bridge. But anyway, basically, the algorithm basically determines what is referred to as the lowest cost port or link, and then it will prune or it will virtually disable the other ports. Okay? They're still there physically, okay, but they're simply disabled. And by lowest cost, what that refers to is not cost in dollars, but cost in terms of what is best. Best is generally defined as the highest bandwidth. So if I should have a scenario where not everything is the same bandwidth, it's going to pick the higher bandwidth because it's better. Okay? Some of the terminology that you'll find has to do with the designated of the ports is either a root port or a designated port or a non-designated port. Non-designated is simply one that is blocked in terms of it's been disabled, okay? And the ports can take different states. And there's also some time delays associated with this. One of the disadvantages of spanning tree is the convergence time, or the time that it takes for all of these devices to basically go through this process of pruning. And at best, it's about 30 seconds. Well, 30 seconds sometimes in network downtime can be an eternity, right? Particularly if your broadcast transport stream, is passing through this. Again, that was a best case example. So as a result, there's several versions now of spanning tree. There was the original one, of course, often referred to as simply legacy STP. Later developed was rapid spanning tree, or RSTP, which, as the name would signify, it's quicker. Well, that's really what the differences primarily are. And then also be aware that once again there is proprietary spanning tree protocols that exist. Just like there was proprietary tagging, there's also proprietary spanning tree. Here's a comparison of some of the different ones and so forth, and where they fit. The practical side, at best, rapid spanning tree will get you down to about 20 seconds, although most of the time 30 seconds is used. And anyway, whereas it's about a minute for the legacy spanning tree. Let's talk about redundant links. Remember this let me go back here to this one. Remember this is a little bit different. I got multiple links between these two switches. What's spanning tree going to do? It's going to eliminate one of them, right? Okay. Let's get back over here. I might want that. That actually could be good. I have multiple links, so I have redundancy, but maybe I want some more bandwidth between these two switches. Okay, wouldn't it be kind of nice to bond that bandwidth together? Okay, and we can do that, and we do that, again, resulting of spanning tree, it's going to prune one of the links by disabling the ports. However, I could use link aggregation or lag to simply expand that link capacity. Of course, there's an IEEE standard associated with link aggregation. Okay. Interesting thing about link aggregation, you'll find a lot of different names for it in the industry. Some of them are specifically associated with particular manufacturers. Okay. For instance, Cisco will refer to it as ether channel. But again, several names that will be really associated with the same thing. And again, the standard just allows multiple physical connections to be bonded into one, and particularly for the NIC or network interface bonding, that's commonly used in server applications and so forth. So again, there is the standard has some terminology associated with it. Typically up to 8 links can be bonded together. Again, there is information, link aggregation, control protocol data units that are exchanged between the devices. That's how they know the status of a link, or if a link disappears for some reason. So also one other thing, they are proprietary link aggregation as well. But again, this is all standards based. Again, there's all kinds of other features that switches can have. Again, I'll call this a short list of features: port security, multicast, the span or the mirror, power over Ethernet. Real quickly, I'll just mention these because we will talk more about security later this afternoon. Again, for now, let's just leave it. There's port security features we can utilize to help secure our network. Okay, pretty easy in most switches to actually implement that. Again, I'll talk more about the details, but basically, because we know a MAC address of a host, we also then can control what host can be plugged into that switch port, or if something else is plugged into it, another host, we can do something. Well, that do something is often, we'll shut the port down. That's not supposed to be plugged in there. Okay, even if someone comes along and plugs something different into it. We'll talk more about that. There also, of course, is multicast. We've mentioned multicast, commonly used in the audio over IP environment. Multicast is really kind of a unique capability because it also starts to kind of bridging standards. It's not clearly, it has a layer 2 component as well as a layer 3 component, and is often considered a layer 4 function. To a normal basic switch, multicast is seen as broadcast traffic, and thus what happens to broadcast? Flooded to all the ports. So you have to have really what I'm going to call a multicast enabled Ethernet switch. What that really says is you must have a Ethernet switch that supports certain provisions of the standards. So in other words, it's a feature set. So you have to have a layer 2 implementation of layer 3 IGMP. Okay? We'll talk about IGMP more, but because Ethernet, remember Ethernet at layer 2, it doesn't see anything above layer 3, but in this case we need to look at layer 3, so they use what is called snooping to do that, where basically the switch simply listens to frames that have multicast traffic, and they quote prune ports. By pruning, we're not now turning the port off, we're just not forwarding the multicast traffic out that port to a host unless that host has been designated as a listener by the IGM protocol action. So again, we'll talk more about that from a little bit later. Also, we might use monitor ports, or in the Cisco world, those are called span ports. I might want to do some troubleshooting, and I'm going to use a protocol analyzer such as Wireshark to do that. How do I tap into the traffic? Well, if I just plug into a port by the normal operation of an Ethernet switch, my analyzer application is never going to see anything, right? Because the traffic's never going to make it out that port, okay? So with a span or monitor port, I can designate port 14 as a monitor port and associate that with port 1 and 23, and now I can see all that traffic, okay? I don't have to go physically put taps in or play all those kind of games and so forth. Pretty easy, to configure so that I can see that traffic. And again, pretty easy to configure in terms of, the command lines to do that. If I have HP switches, same principle, okay? And a different syntax of my interface, but again, pretty easy way to do that. I'll mention PoE again. We talked about PoE at layer 1, right? That really was kind of focused on what? Current and wiring and that sort of thing. We also have a component of PoE at layer 2, and it has to do with the detection side. And with the detection, there's an algorithm or a flow of, first, we don't apply DC power to a port that has a host device that doesn't need PoE. You don't just put DC out on the end of that network cable unless it's needed. If you do need it, then it has to be classified. What kind of PoE does it need? Remember, there were several levels of PoE. The difference was what? Current. So I don't, in other words, put more current than is really needed out there. And of course, if I have a host device then that goes away that's using PoE, what I want to do? I want to, shut down the DC at the switch port. So there's a fairly complex algorithm that is done with that. Again, terminology associated with how do I generate that. Such a Ethernet switch that has PoE is referred to as an N-span PoE device. That power injector, remember that we could use externally, is referred to as a mid-span power injector or a power source device. And again, this fairly complex algorithm with time factors that does the detection and the classification. Even the startup. The startup, you don't just turn the DC on like a switch. It actually ramps the voltage up, because that certain just turning the switch on could put a spike in the data, which would in turn corrupt it. So the voltage is actually ramped up.
You get a spike when you turn on phantom power on a mixer.
Well, yeah, that's a good example. That pop that you get, right? Well, in the data world, that pop, what is a disruption of the data?
The PoE port, I guess, on an expensive switch can actually current limit the ports to a different value depending on what it thinks.
Yeah, it detects what's out there at the other, what standard device is out at
Oh,
the
and
other
it does
end.
it based on what it sees on the
Yeah,
other
because
end.
remember the difference in those three standards had to do with the amount of, the spec is in wattage, but we know wattage translates to the amount of current that switch is by, because the voltage is effectively the same. It's effectively 48 volts of DC. The standard PoE voltage is 48 volts. However, if you look at the details, the range is a little bit wider on some of the newer standards, but it's nominally 48. It's nominally 48 volts. Another one of the protocols that we mentioned was Precision Time Protocol, and simply as the name implies, it is simply a time protocol, somewhat similar to NTP. It's just more accurate. In fact, it's down to the nanosecond and can be to the picosecond accuracy. It has a hierarchy to it. So the grandmaster, that's like the master clock, that you might have in the facility, uses UDP multicast distribution. We haven't talked about UDP yet, so we'll get to that a little bit later. It also uses what is called the Unix epochs, which, are you familiar with this term? Okay, it's a time standard developed back when the Unix operating system was developed. It uses a reference of January 1 of 1970. And basically, it's counting seconds. And when I put this slide together, it was done on July the 19th, because I try to refresh this kind of stuff in these slides. And I don't know what time 1559 GMT is. I have to use my little dual clock. Okay, so I guess instead of working that afternoon, I was playing with slides in the office, and I grabbed, the current value of the epoch. So I can take that down to the picosecond level and tell what time it is from that. So anyway, that's PTP, and again, it is it was not really necessarily developed for broadcast. Well, it was and it wasn't. The principle of it was developed actually for audio and video media on a network, because it is an IEEE specs, but it's been adopted by the broadcast industry. And I think SMPTE even has a standard reference that is 1588. Is that's yeah. And they have their own SMPTE, and I can't remember the number. Yes, version 2. Yeah, also referred sometimes to as 1588-2008, which is version 2, which is basically more accurate. That's how you get, I think, to the picosecond level with. LTE in the context of the cellular, I can't answer that one.
It's actually used in digital audio to make sure that the packets are all lined up, and they feed Dante and all the different people use PTP version 2 because it gives them nanoseconds and picofarad picoseconds right to so they can line them up. So that's what they
and
use.
it does this by basically it timestamps the timestamps puts a timestamp that also allows you to put the packets back in the right order at the other end too.
It's sent approximately every 10 seconds, I think. As I recall studying that, it's a packet that's sent right along with the audio packets, and they send it out about every 10 seconds, and it's just a stamp that locks your local clock. Every device has their own clock, and all this does is just lock, like the old stuff you used in TV, you know.
This is it's kind of the modern time code, I guess,
That's right.
where you have a master. It's called a grandmaster, which in a lot of cases that sort of looks like the GPS time code clock I have. Okay. But you have, a device, again, it's generating that. Also, generally, these devices also do NTP as well. Usually, not usually, they are going to be GPS locked and all that. And they have kind of three levels. An ordinary device is really the end host device. But you can have what is referred to as boundary clocks that are then referenced to a grandmaster, and in a large broadcast facility, you very well could have several boundary clocks throughout a facility that are all referenced to the facility grandmaster and so forth.
It actually takes the place of the word clock. In regular digital, where you had to send a word clock to lock all the devices together, when you switch over to IP, you don't send word clock anymore. You just send a packet right along with the audio data, and that inside that one particular packet has the PTP information.
Yeah. Okay, and to wrap up, remember our basic network model that we started with. We've added, a couple of layer 2 devices to it. And to expand that, if we think about our encapsulation and de-encapsulation, a layer 2 device is only going to de-encapsulate up to layer 2. Re-encapsulate, make some bits, send it across the network, the same thing through each device. So what that says is everything above layer 2, that switch does not see. It doesn't know it's IP or what. It doesn't really care. It only cares up to layer 2.
I had one question about VLAN. VLANs are not restricted to a particular area. Like in a studio, you can have a VLAN, but that same VLAN can extend through the public network to maybe you have an office in Birmingham and another one in Baltimore.
That's right. I could have that VLAN can span. Yes, it can span multiple locations.
And this is the way you do it with your transmitter situation. You can have, and most people now, especially the people that talking about the audio data and getting into the transmitter, they recommend that you set that on a VLAN. And so you can have VLAN 4 running in the studio with all your automation equipment, and that can be extended out to the transmitter and still be VLAN 4. So you've got all your data, and that seems to be the best way to do it, is put everything in the same VLAN, even all the way to the transmitter.
Yep. Yes, very, very much so.